event that we're having here. And as you see on your screen there, it is being recorded. This is the second of a three-part series. And so mark on your calendar for May 18th, that's going to be the third part to this series as well. So we're excited about this. Once again, this is being recorded. And this event is really brought to you, these three events by SLM. The knowledge and the expertise that they have in additive manufacturing is second to none. And we're so grateful that they're here sharing their information. The first one that we did back in March was really kind of a general overview of additive and how it fits in the aerospace industry. And I'll be sharing a little bit more about what we've got going on today. But here's the quick agenda. So we're going to have a welcome. We're going to have a few opening comments and sharing about some of the upcoming events. And then we're just going to dive in. We've got a real treat of a presenter I'll be sharing with you here in a few minutes. And we want this to be engaging. So we literally have one of the brightest people in additive manufacturing in the US sharing with us today. And it's going to be a lot of technical information. And as you've got questions, please just write those in the chat. Anything at all. Doesn't matter what it is, your question about additive manufacturing. Today is the day for you to ask those questions because our presenter is going to be able to answer them for you. And he just loves this stuff. So we're glad that you're here. And then we'll save a little time at the end also. If you got a bigger question or something that comes to you late in the presentation, take note, and then we'll have an open Q&A at the end where you can ask questions then as well. And then we'll just do a little wrap-up following. So we'd like to take a minute to thank all of our corporate circle sponsors. These are the different companies out there that help make PNAA possible and all the different programming that we deliver throughout the year. We've got many events each month now through the end of the year. So we'd like to take a moment to thank those that are supporting us financially. Boeing, Snohomish County, Payne Field, Moss Adams, ProShop, Sekisui Aerospace, Orion, Deal Aviation, Cyberstreams, Impact Washington, Northwest Aerospace News Magazine, Ajax, CG Tech Faircut, and Baker Hostetler. And we would like to thank SLM once again for sponsoring and being involved with PNAA in such a deep level at the conference this year. So hats off for the great partnership, and thank you SLM for helping sponsor this today. This is our 20th anniversary. If you hadn't heard at some point, PNAA is turning 20 this year. It's hard to believe. 20 years has gone by supporting aerospace manufacturing in the Northwest, helping make it competitive. But this doesn't happen without all of you being here. So thanks for being here today. And thanks for attending our events and making what we do possible for the industry. Some of our upcoming events, this Friday at 12 o'clock, we're going to be doing a Factory Friday virtual tour of technical tooling. And if you've not seen what they're capable of, it's pretty fascinating. Vacuum forming, molding, fixturing, different parts that go into the production system that sometimes we don't stop and think about. They've got some amazing capabilities. So check that out. More information on our website if you'd like to learn more. Once again, also mark on your calendar the third part to this series, May 18th. So that's going to be next month at 12 p.m. Pacific time. And we're going to be joined by Jonas Mersch. Jonas is going to be sharing about SLM's new flagship additive manufacturing machine, the NXG 12600. This is a 12 laser, I think 1,000 watt per laser, Don will correct me otherwise, system. And it is the flagship of what's out there in additive manufacturing for metal additive today. And they're going to be talking about that and some of their other technologies. So mark your calendar for that. A few days later, we've got our 8th annual Women in Aerospace, and we'd like to thank all of our sponsors that you see there at the bottom of the screen for participating. This is going to be quite the event, an event of inspiration, of storytelling, and we're going to be doing some fun things this year, like a hackathon where groups will be broken out to create solutions to real-world problems in the workplace. So invite your friends and your folks and colleagues out in the industry to Women in Aerospace, May 21st. And then we're going to have June 10th, our 9th annual Aerospace Defense Conference. And we put that together with PNDC, and this year with PTAC and NASA and the Washington State Space Coalition. We're very excited about this. Thank you to our sponsors down below there. One of the features of this event this year will be a B2B matchmaking, so one-on-one type sessions with some of the NASA primes, companies like JPL, Lockheed, some of those. So we're very excited about that. That will be also an all-day virtual event. And then, as I've just shared with the folks on the call before, we're launching our first annual Aerospace Technical Conference. And so this will be July 13th. This is a one-day event. We're hoping it will be in person. We'll see based on COVID. But this will be really designed for the production staff, your production managers, your engineering departments. We'll be talking about software, CNC driving, all different types of activities that are very technical in nature. And so stay tuned for more information on that. So once again, big thanks to SLM. They really support PNAA and aerospace manufacturing here in the Northwest. They've got a vested interest in the industry, and specifically here in the Northwest, we believe there's a lot of opportunity for metal additive manufacturing in this region alone. And so it's great working with them. Today's event's designed to be interactive. So once again, type your questions in the chat box there, and I will ask those. And so we'd encourage you to do that because we've got some great information. Today it's my distinct pleasure to recognize, thank, and introduce Donald Godfrey. He's the Senior Fellow Aerospace and Defense Additive Strategy for SLM. And Don, I'm sure will tell us how long he's been in additive, but Don is one of the most knowledgeable persons that I've met in the country when it comes to additive. He spoke at our annual conference this year, and I don't think anyone's got a question that's going to stump Don today, but that would be really neat to see if that were the case. So feel free to add those out there. And with that, Don, thank you so much for being here. Emily and the entire team from SLM, we appreciate it. And Don, I'm going to hand it over to you.
Okay, let me share my screen, and this should do it right here. Do you see the PowerPoint presentation? Okay, great. So today we're going to talk a little bit about material qualification. After you buy your machine, you buy your powder, and you have your process developed, what does it take to get FAA approval or your company's approval to put that printed part on an aircraft? So let's talk about that. Little bit about me. All right, so one of the 6 things we're going to talk about, or 5 things we're going to talk about: why do we have to perform material characterization? What does that involve? What does it cost? How many different alloys? And when people talk about AB basis, what does that really mean? And then we're going to wrap it up and have some questions and answers. So why do we perform material characterization? We all know this, it's obvious, but let's just state it, that our industry is a risk-adverse industry. Designers must have material property data or material strength data so components can be designed without the fear of failure. Customers, insurance organizations require accurate engineering and science be designed. Be applied to our designs. It's unrealistic to think that we can design something without knowing or understanding the expected life of a component. And with additive being new and novel, we need to have that engineering data. And we must understand that culture and the perception of risk are the greatest hurdles that additive manufacturing has. We've all heard that saying, culture eats strategy for breakfast. And I saw this firsthand with, I spent 11 years at Rolls-Royce Propulsion and 14 years at Honeywell Propulsion. And it's very difficult to change the culture of these large engineering organizations. If somebody who has been involved with casting gearboxes for their entire career and you try to convince them, hey, we should print this, you're going to receive a lot of pushback. Organizations not familiar with additive will avoid using it due to risk mitigation. And so the science of additive must prove the mechanical properties are as good as or better than conventional manufacturing technologies, i.e. castings, weldments, sheet metal, and etc. So what is involved with characterization? So we have to prove to our customers, and that the customers may be your Boeings, your Lockheed Martins, your Airbuses, but eventually it will become the DoD and the FAA, that you have processes under control for powder, shielding gases. Do you have a fixed process for your printing? And can you validate the tensile quality, the tensile strengths, the LCFs of machined versus as built, or high cycle fatigue, machined or as built, or creep? And there are other tests in there as well, but I just mentioned those. Before you begin the characterization, you have to prove that your process is repeatable, meaning you're going to print 50 to 100 tensile specimens on your machine, and they're going to give you an average of X KSI, whatever that is. You're going to do that exact same build another time, and they must be repeatable. You have to be within plus or minus 3 sigma of the first round. Now, companies in the United States typically use an ASTM specimen, like an E8, and in Europe they'll use a DENT specimen. But those values should be correlatable. You must have fixed non-variable manufacturing processes. Now, they can be internal, because if they've been in printing additive for a while, the ASTM and SAE specs were not available. So some companies will have internal documentation or internal specifications, and some will have a mixture of both. But they must be auditable, meaning the FAA will come to your facility and they will look at those specs and they will look at your process, and to validate that you're following the process. I've been involved with 3 of those. And one of the funny ones was the FAA audited us on how we audit our suppliers. It was kind of interesting. You're going to have a powder specification. Again, the public specifications are coming out, but if you've been doing it for a while, you're going to have probably an internal one. And you must have access to some kind of material property database. It could be internal. They're looking for MMPDS type data. You may or may not have that. I was, not too long ago, I was in California visiting a defense contractor that's printing a lot of components, and they just flat out said, we have our own database, we're not going to do MMPDS. But we're going to talk a little bit about that as we go through. There are some aerospace companies that if you print for them, they're going to require you have MMPDS. But it's going to vary customer by customer. Now, I showed you a list of some testing. Remember that not every test needs to be performed for every application. The requirements of the design determine what testing that you do. All companies that incorporate 3D printing are going to have some kind of material characterization program. Those companies may or may not have MMPDS A or B basis type of data. And it's important, you also vary the testing on the type of alloy. So with aluminum, one of the big tests that people like to do is oxidation tests, which is not on that list that I showed you. So when we talk about powder, one of the things you want to know is your source of powder consistent, and you typically look across 3 or 4 heats. What's best is if you use multiple vendors, but the key here is, let's say you buy powder from, I'll pick a company, Praxair, right? One of the things you want to do is make sure that the chemistry and the morphology of the powder is consistent and repeatable, right? And you don't do that by looking at their material data sheet. You send it out to a lab like Element or Westmoreland or whomever, and you have the chemistry and the morphology checked. And what you're looking for is repeatability. You must show data comparing one laser to dual lasers. One of the advantage SLM has in the marketplace is that we have really done a great job with printing parts using multi-lasers. And I'm going to show you a video in a little bit of printing a part with 12 lasers. There are internal processes, or your internal processes or your supply chain have to follow some kind of standards. Now, some companies write their own standards. You also have SAE, ASTM, ISO, AS9100, and NADCAP. So that's internal on which processes and standards you follow. All right. So how do we control the powder source? And we'll just start at the very beginning and we're going to go through the end. When it comes to nickels, or titaniums, you almost always use vacuum induction melting. And it starts with collecting the elements. When you go to the atomizer, you will see buckets of different elements, and they literally weigh those buckets individually, and they set it up by percentages. So you put the elements into the chamber, you melt them, then you pour them and you atomize them. They'll heat this, and they will, once it's in the melted state, they'll take high pressure argon and blow it through, or push it through this chamber. It comes out in an atomized state, and then we collect it. All right. Powder is in a VIM system. It's always in a vacuum, so it's a very tall building that you're going to do this in. So as I said, now this is for 718. I just got this off the internet. And you're going to see your aluminum, your boron, your copper, chromium, iron, and they're going to weigh, they're going to have a bucket of iron there, and it's going to be 17% of the total weight of all the buckets. And each one of these elements will have their own bucket. So after you atomize it, you get this 1,000 pounds of powder at the end. And this powder is going to have a lot of different sizes to it. So if you're using electron beam, you're going to use powder in the size of, this is going to be in the what is this, 100 micron size area. DED is going to use, they can use a lot of the larger size powder. The smaller powder in the 22 micron to the 5 micron is going to be used for binder jet. And then the laser powder, it's going to run in the 50 to the 11 micron area. Powder companies like to tell you they atomize all this and they only get a small window. That's a half truth, right? And that they're telling you that to justify their pricing. The truth is they sell all of this. They just sell it to various customers. And you're focusing on, with laser bed powder, you're focusing on this blue bar here.
Hey Don, what's DED?
Direct energy deposition. There's a company in South Dakota that makes these machines. I can't think of the name of them right now. Robert Morris, I think. And then there's one in Albuquerque. But basically, they take blown powder. They take powder and they push it through a hose with argon, and it falls into the path of a laser or an electron beam, and then they build it up that way. A company that does a lot of work like that is the rocket company in LA. I can't think of their name right now. I'll tell you if I can remember it. But that's really what that is. So but you lose a lot of fidelity with DED. So sometimes companies use wire instead of powder. So with powder, you can hold a dimension plus or minus 5 thousandths. With DED, it's going to be plus or minus 25 thousandths. It's a huge delta. So you use DED for speed. That's going to be machined down later. You use powder bed for fidelity. So for example, if you're doing a gearbox with oil passages, you would never use DED because the oil passages would just be a disaster. But with powder, you can print that. Okay.
Thank you, Don.
Sure. So the way we do this is we atomize the powder, we sieve it, like I said, and then we inspect it, and you get a lot of powder that has to be segregated and sold off to various customers. Now, with cryogenic gas, meaning argon or nitrogen, those are really the two gases that are used. It also is done in a vacuum, and we compress the gas and we release it to turn it into a liquid. And like oil and water, the heavy elements fall to the bottom. So when you do this, nitrogen, being the heavier element, will fall to the bottom of a tower, and hydrogen goes to the top. And then we have pumps in these towers where we pull off the liquid nitrogen. And then as it depletes, the argon, everything starts to fall. And then when that's done, it is stored in large vessels. So this tank, this is a picture from Lindy, it will not be multiple gases. It will only be one gas. So you'll have a tank of argon or a tank of nitrogen or a tank of helium. But it is done through the stratification process. It's very expensive. But from a perspective of quality, what you're looking for is what is the quality level of that gas. So if you were to buy a tank of argon, we call that's established to United States Pharmacopedia standards. It's called 5 nines. So it's 99.999% pure. Typically, when you have a large tank like this and it comes to you in a truck, they will advertise it is 99.995% pure. Both will probably work. The 5 nines always works. It depends on what you're doing with what alloy. But what you want to control from a quality standpoint is moisture pickup. Is the moisture in your gas minimized? Because that will play a very important role in things like aluminum, titanium, and tungsten. Not so much with nickel, but with those three, it very, very much is. And so you have to control that. And you'll be expected to measure it to get your qualification. Now, when you do this printing, what you really want to do is 10 powder lots. And what you're looking for are you going to get the same mechanical property data from each powder lot. And this is one way of stratifying the market for powder companies, right? You can get 10 powder heats from the same company. You can do that, but that testing could take you a year to do. Or you could go buy powder from 10 different companies, and by default, you get 10 different heats. It's always great to have multiple machines, and then you're going to have a discussion with your material science people and your structures people and your engineering group. How do you want to test? Now, to get MMPDS, you need to do 300 specimens. So let's say you do 300 tensile specimens. There is a debate, and it hasn't been decided, should those 300 specimens be at the same temperature? But you're going to do room temperature, which is 75 degrees F. And you're going to, what I've typically done over the years is I jump up into 200 degree increments. So I think I built this just as reference. It's not going to be aluminum, but for nickel, you may test all the way up to 1900 degrees F. But you're not going to test a lot. You may do 20 at that. And what you're trying to do is fill out your curve. Most of your testing is going to be in the 600 to 1300 degree range. With aluminum, it's going to be room temperature to, you might go to 600 degrees, but maybe it depends. So you're going to do tensile as printed. And another thing, if you're doing Marium 247 or some Haynes alloys, you want to know, is there an orientation effect? So you're going to test the same number of verticals as you do horizontals to see if the material has a material property variation based on the orientation of which it was built. I can tell you with things like 625 and 718, you're not going to see more than 2% orientation effect. But with Marium 247, 738, and some other alloys, you most certainly will see a major swing.
Hey, Don, quick question for you.
Uh-huh.
So when we're talking about testing the powder, is this something you kind of do once when you get the machine, or does every lot, or I guess a heat of this powder, you need to test every lot of it, or can you explain that a little bit more?
So the way we set it up, we being the Honeywell organizations, was that when powder comes in, we take so many grams of powder, typically 100 grams, and we send it to a testing house, and they test the chemistry and they test the morphology. We also do it internally, but we want an independent source. So from that perspective, yes, you do it each and every time. Yes, the company that provides the powder, they say they inspect it, but they basically are going to give you a sheet they printed off 6 months ago, and they're going to stick it in the box and say that's what you get. You have to be certain. And yes, we have caught powder companies screw ups where the lab results did not match what the powder company said it was. So they're learning too, right? They're just not accustomed to these standards. They're used to selling powder for metal injection molding, for maybe MIM applications, for automotive applications. And so you have to also work with your powder supplier and train them how to do this. Every powder company thinks they know how to do this, but the truth is very few of them do. And that they have to go through the process. So yes, now when you get into applications where you're doing powder reuse, which is a total nightmare, you have to do it each and every time you reuse that powder. So that it becomes a logistics problem, but Yes, the answer to your question is yes, you have to do it each time.
Okay.
So one of the things SLM is really, really good at is multi-laser applications. And we have multiple projects going on right now with various universities and DoD industries, organizations, I should say, in North America to validate this on a public forum. So, and this is a typical SLM 500 machine where you have 4 lasers. But in between these dotted lines, you have dual lasers. And so what you have to prove to your customers and eventually your government regulatory agencies is, does laser 1 produce the same mechanical property strengths as parts produced in laser zone 2, laser zone 3, laser zone 4? Then you have to ask yourself, are we producing the same mechanical property strengths in these overlap areas? So you essentially have 7 areas that you have to validate. Okay. So in this type of format, you can print a very large part, or you can print lots of little parts. But you have to validate each and every one of those lasers. Now here is a typical, and it's not typical, this is our NXG machine with 12 lasers. And this build platform is 600 millimeters by 600 millimeters by 600 millimeters. And it was designed to print low volume castings. Right. I hope you're catching that.
Yeah,
now you
Don,
can
can you explain kind of what we're seeing here? What's going on exactly?
All right. So this is a very, very, let me run it again. Mm-hmm. This is a very large part. And one of the tricks in doing this is, are you able to control the overlap areas with 12 lasers? And can you control the amount of debris, i.e. smoke, soot, that is being generated across a large platform? Because it's not so much, I have seen this on other machines, if you print to the left side of this, the smoke gets absorbed or exhausted out. But if you're printing on the right side, the soot has to travel 5 times as far. And how do you control not letting that soot fall on the part and being absorbed in the next layer? So in this particular case, this is an aerospace component. I may or may not have a picture of this in this presentation, but we have sold 5 of these to a high-end automotive company in Europe. And there's one of these machines sitting in California right now. So this is what you're going to learn about in the next webinar, which is the NXG 600. All right. There we go. So as I said before, we're going to standardize on a specimen. And typically in the United States, we do an ASTM E8 specimen, which is 60. If you're doing a horizontal, it's 600 thousandths in the X and the Z, and then it's 3 inches long. In a vertical, it's just a cylinder. So as I said before, we're doing a lot of testing here. So this is the first platform we did for Hastelloy X, and we're doing this with NASA. And we were one of the, and maybe the only company to print this alloy without microcracking. Hastelloy X is a very, very difficult alloy to weld. And our friends in the space industry and the University of Auburn have run every one of these things through a CT scanner and found 0 microcracking. So we're very, very pleased with that. And those test results should be released very, very soon. And they become immediately available to SLM customers. Now, we're working with the US Air Force and NASA and some other people on F-357. And we're also working a new heat treat. So one of the problems you have with aluminum and printing is dealing with HIP and how you heat treat it. And so I just got the test results back today where we improved the yield by close to 50% and the ultimate tensile strength by nearly 100% over the conventional stress relieve only approach. One of the problems you have with printed aluminum is how do you heat treat it, HIP it, and water quench without getting distortion. And we've been able to do that. And so those papers will come out within the next 60 days. We're very excited about this. We're doing a 316 build with some customers and Penn State University. Those papers should be released very, very soon. This is our first Ti 6-4 specimens. We're working with 2 defense contractors on the West Coast and University of Arizona. And that's a typical, so one of the reasons we like to use the 500 and the 800 machines is because all of these red areas are overlap areas where we're using multiple lasers. So not only are we doing these alloys, but we're comparing single laser printing versus dual laser printing. Because SLM really is very, very good with controlling material properties using multi-laser applications. And when all this is done, when all these reports are finished and all the white papers are published and presentations are made, they go directly to our customers. And we need to point out here that Element and Westmoreland and these national labs are the ones doing the testing. It is not SLM. I wanted an independent source. And I don't have a picture of it, but NIST is working a very interesting 718 project. So we talk a little bit about characterization. Well, what does that really cost? How much do I budget? A typical room temperature tensile is $130. Elevated temperature, typically in the 200. LCFs are going to vary all over the map because you don't know how many, you have to set a failure rate. So is that going to be 1 million? Is that 10 million? But you should plan on spending $500 to $1,000. And the same is true with HCF. Creep, depending on how you set the resistance, but you don't want a creep test going 2 weeks. You just can't afford that. But you should be thinking $2,000 a test, all right? So then the question comes up, how many do you test? Because if you test 100, that means you're going to spend $200,000 just on creep test. So you also have to budget the cost of the engineer / metallurgist in interpreting the data. I've done several different alloys. You're not going to do it for less than $1 million, and you probably should be looking at $1.5 million to $1.8 million to get a fully characterized material database. So that's one of the reasons that SLM has partnered with the Air Force and NASA and Office of Naval Research and these universities and the Battelle Institute, is that we're going to do this. We are doing it now, and we're going to give it at no cost to our customers. So then you go back and you ask yourself, okay, these are the tests that I have to do. What is my budget? And your budget is going to control what tests that you're going to do. Obviously, no one's going to do it for free. So you have to go back to your matrix that I showed you earlier and look at it from a budget perspective. What are you going to do? Maybe you cannot afford to do 10 powder lots. Maybe you can only afford to do 3 powder lots. Maybe you don't do 300 tensile. Maybe you do 100. But that's where that's going to be key. You got to do this, and it's based on how much money you want. So then you ask yourself, well, what alloys should we do? And if you look at the aviation industry, typically they're doing 718, 625, Ti 64, ALSI 10, F357, some coppers, right? Some people will tell you we want to do them all, but those are the people who really don't understand what an engineering budget looks like. You have certain alloys, and if you're spending a lot of money for each one of those that I mentioned, a lot. Now, in the automotive world, you're not going to have to do as much testing as you do in the aviation or space world. Industrial gas turbines, they're really not focused on aluminums or coppers or titaniums. They don't care what their stuff weighs. So let me go to the next slide. These are the alloys that I believe are, and I surveyed multiple companies in the past 6 months across Europe and the United States. And most people are doing 625, 718, cobalt chrome, 939 is picking it up, 230, 282. When you look at stainless, the 17.4 is typically in the military, the oil and gas industry, 316, aluminums. You're seeing a lot of these RAM, 6061 RAM, 77A7. These have great strengths at room temperature where they fall down, and they're great alloys, they really are. But when you do with any aluminum that you test, you have to test for oxidation. NASA is really big on this GROP 42. That's a new copper alloy that is being pushed hard by our friends at NASA. And then titaniums, tool steels, specialty steels. Tungsten is big in the space industry for satellites. And then 6242 is coming on because it's a higher strength titanium. That's a very tough alloy to weld because of moisture content in the argon and the oxygen content in the build chamber. That takes some special handling. Now, you may hear A and B basis, and what does that mean? So when someone has, let's say you have 2 databases of material property data. B basis is that you have at least 90% of your population sample or your database exceed some value, and you have a 95% confidence in that data. And you might use that for a bracket, right? A non-life critical part. Life critical, meaning that if it broke, you're in big doo-doo. It's going to endanger the life of the mission. A basis, you have 99% of the population equals some value, and you have a 95% confidence in that data. Sample size and type of testing is going to be key. Typically, when you have that type of data, you're going to have at least 300 test specimens, at least 300. So it can be expensive. So who is and who is not? All companies that incorporate 3D printing have some kind of database, right? And we are just now as an industry getting to the point where we can say with confidence we have either A or B basis. But up to this point, it's been very difficult. The amount of data generated may or may not be A or B, AB basis level. As I said, I was with this aerospace company in California, a multi-billion-dollar organization that said they're not going to do it, right? They have confidence in their own data. Large corporations printing components for internal use, they're going to have some kind of database. Government agencies like NASA, the DoD, they also have databases and they're building toward AB basis. But most companies are using self-qualification approaches, meaning like the company in California, I have 150 specimens, I have 200 specimens. That's good enough. I'm not going to do any more testing. So in conclusion, the aviation space industry is risk adverse. We all know that. We work it and live it every day. Change, no matter what it is, equates to risk until the manufacturing processes are totally validated, meaning you're validating your powder, you're validating your gas, you're validating your printing process, and you're validating your post-printing processes. Material property databases must be created for designers to implement additive. Otherwise, they're just shooting in the dark. And the function of the part determines the size of the data needed. An A basis database is going to cost you $2 million per alloy. And with that, I open it to the floor for questions.
Very good. Thank you, Don. Wow, good stuff. We got a smaller group. Maybe we just go around the room and I'll call your names. And if you have a question, feel free to shout it out. So Craig, obviously some interesting stuff, on the thermal properties here. Do you have any questions that you'd like to ask Don?
Not at this time. I'm just real curious to see these papers when you release them. It'd be some interesting reading. So I'm excited about that.
Okay, I'll make sure Brian gets them and he can circulate them to whomever, his whole organization. Why not?
Thanks, Doug.
Yep.
Perfect.
Yep. Cool. How about down in Portland there, Brian? Any questions or comments, feedback?
Not really. I'm still learning about this process. I know the basics and trying to get a little bit better educated on it. No real questions at this time.
Right. Well, let me invite you to Wixom, Michigan, and you can come take a tour of our facility and sit with us, and we'll try to answer all your questions right next to the machines.
Excellent. If you find yourself in Portland, Oregon, come by Grove Tech Machining. We'll show you our screw machine shop.
Okay, great. Thank you.
Cool. Excellent. Dale, you've been the maestro on the technology today. Any questions for Don on additive? And you're on mute, just to let you know. Still on mute, Dale.
No, I don't have anything to ask as much as it's fascinating to watch. I was involved with 3D part printing in metals 20 years ago. So Don's seen a lot change, and but it's been exciting, and it's great to see it come to this level.
Okay. Paul, any questions?
No, I would really like to go see that machine in operation, though. That would be interesting to watch it. Can you see a part while it's being built, Donald?
You can see the top of the part. So you imagine, if you will, a part that is 10 inches tall, right? And it's going to take 8,000 layers to build that part. So when you look in the window, you are looking at 1/8,000th of the part, right? So you're really just looking at a slice of the part in the vertical orientation as you look down on it. So you don't really see, like if you go back to that video I showed of 12 lasers, that particular part is 570 millimeters tall. All right, but you're seeing just a slice of it from the top perspective.
And are you saying it's building 5,000ths at a time?
Oh, no, see, I'm going to go to microns for you. We're building 60 microns at a time. I can't sit here and tell you how many thousandths that is, but yeah, and typically it's a few thousandths tall. Okay. And you're seeing that, just that one layer. So if you had a part that, I'll just say a pyramid, right? When you print at the very bottom, you're going to see a huge welded base. But if you go to the top, you're going to see lasers just weld the very top, right? So it's hard to imagine what the part looks like looking at it one layer at a time.
And Don, correct me if I'm wrong in this, but let's say a layer gets built. Then there's that big arm that you saw in the video, I believe it's called the recoder. Mm-hmm. And it brings a thin layer of powder over, and then the laser then welds the next layer on top with that powder there. Is that correct?
That's right. That's right. So depending on the power of the laser, you're going to weld not only that 60 microns of powder, but you're also going to re-weld the 60 microns of powder that you just welded. And that's how they get the strength of getting your tensile strength into the part itself.
Good question, Paul. Thank you.
Again, come to Wixom, and or maybe we can find there are companies in Los Angeles that have our machines. Maybe we can all go down there and give a tour here. You can.
I think there's some here in Seattle too. Maybe Winthrop can connect us up.
Yeah, well, I'm not supposed to talk about those.
Oh, okay. That's fine. Okay. That's great. Well, with Siemens, we've got Steve Aubrey here. Steve, obviously a fascinating presentation. Any questions from you, sir?
Yeah, Don, good to meet you. I'm with Digital Industries, and you probably know a couple of the folks that I work with through our organization dealing with controls. Tim Bell, who's our additive manufacturing business manager out of Cincinnati, he works on the controls with you guys and a lot of other manufacturers. And also Tad Steinberg, who's with Siemens Energy out of Orlando.
Yeah.
He's business development for that. So, and I've also interfaced on your side with Winthrop and also Josh Brown in different meetings and such. So my background, I'm a structures engineer, and I've done a lot of testing in the fasteners arena. So when you went through the portion about the testing and all the different alloys and the number of specimens and all, that was spot on. And you're very accurate that it takes millions of hours of tests to add all that up to develop that. So that's really critical in the fastener world. So very interesting presentation. Look forward to the third one coming up. I don't have anything further to add to that, but we do enjoy doing business with you guys as well. Thank you much.
Great. I've known Tim since 2006. I've been to the Siemens facilities across England and across Sweden as well. I can never say it. Is it Fishbach?
I don't know the name myself.
Yeah.
Tim is opening a brand new demonstration center, I believe, in the Charlotte area, if you were not aware of that.
Mm-hmm. Okay, very good.
So he's put it out on LinkedIn recently. So anyhow, again, thank you very much. Look forward to your next session.
Thank you.
Thanks, Steve. How about Aaron Herringshaw? Any questions for Don? Erin's on mute. She may be away.
I'm
There you
sorry.
are. No problem.
No, I was sitting here watching and thinking I took a lot of chemistry and I really liked it, but this is way beyond my capabilities. It's been too long, but I'm so glad to be exposed to it because it's not a world I get to see very often anymore.
Right.
Thanks.
Yeah.
Yes. Very interesting.
Thanks for being here, Erin.
Yes.
Great. And we got Dave Nave with Dave Nave and Associates. Dave, any questions for Donald today?
No, I don't. I'm just like the other people. It's been a long time since I've talked at this or heard anything at this level
Yeah,
of knowledge, and it's really fascinating.
it's great.
But
Cool.
it's been a while.
Yeah.
Thank you. Appreciate it.
Yeah, you bet. Thanks for being here, Dave. We've got Robin Toth, Washington State Department of Commerce. Robin, if you're there, not occupied, do you have any questions that you'd like to ask today? She may be tied up with something, but we'll circle back with her if she comes back on. And how about Chris Mann? Chris, thanks for being here today. Do you have any questions that you'd like to ask Don today?
Hey, Brian, thanks. Sorry I missed the introductory portion at the beginning. I had a customer walk in on me.
Oh, no problem.
But yeah, I mean, it was very, very informative. I'm very new to metal 3D printing, and I did have one question for Donald. So in my experience with like plastic printing, where if you don't design and build your own support structure for something like an undercut, you know, you're going to have a lot of problems with the part sagging. Is there anything similar to that with metal printing? Anything that would affect form?
Yeah. Up until recently, you've always had to use the Magic software or build it into the CAD file itself. Some kind of structural support. You know, 3D printing is a lot like Hollywood. None of us like the effects of gravity, and if you don't put the support in there, it's going to sag when it's in the molten state. Now, granted, it stays molten for what, negative 10 to the 6th, but that is enough to cause distortion and collapse because gravity is constant. Now SLM is coming out with a new technology, and you'll see it probably in the next 30 days, I think, is the release. It's called Smart Vector. And what this is a technology through software that allows us to print overhangs with no, or at least minimalized support structures. And that's going to have a big dividend for particularly in internal geometries where it's difficult to get support structures removed. And what this software will allow us to do is print things like oil passages or cavities without the need to go back in there and clean that up. It's going to be a big advantage for the metal industry. But you're right. And for the last decade, we've had to use support structures, and it's a pain. It's a necessary evil, but we're trying to get away from that. And I think we're going to make good progress this year.
Gotcha. And is there like a go-to solution when you guys are, and just as a background, I work with a company called Capture 3D. Brian, you may have known my boss, Staten Apple, or Kyle Kennelly.
Yep.
I'm new to the office up here, so it's my first introduction with PNAA. But we work with 3D scanners, so that's kind of our piece of the pie is when people are having form issues, whether it's caused by deformation from over the overhangs or something like that, or maybe heat treatment, whatever. We're trying to help measure exactly how much it's deformed so that we can feed that back in to the system so that it can be compensated for. Do you guys have like a go-to solution for that?
Typically, okay, so I'm going to answer this. Typically, companies like Pratt & Whitney, Honeywell, NASA, there are softwares out there that they select. SLM does not sell that type of software.
Gotcha.
You're right. You could print everything absolutely perfect, and once you heat treat it, particularly aluminum, it comes and moves 20, 30 thousandths, and you're frustrated. And the way to prevent that is you white light scan it after the distortion, and you make calculations how to move the CAD file, or you start adding support structure to be removed after heat treat. And aluminum, its most predominant issue with aluminum, and so that's why I'm really super excited about what I told you in the very beginning, how we've come up with this new heat treat where we eliminate the need for water quenching of aluminum, and we still get T6 type properties. And but what you do is very, very important for all of us that have to print things to maintain a geometrical dimension, because I don't feel comfortable straightening a printed part. I don't, even a casting. You know, distortion has always been a problem with aluminum, because you water quench typically, or you do a glycol quench. So getting away from that is a big thing.
Gotcha. Thank you very much. Appreciate it.
Sure.
All right, Don, I think I'm up. I've got a couple of questions for you.
Okay.
So maybe we can go back to testing a little bit. So what wasn't super clear to me is, let's say I get a customer, they want me to build an aerospace part. Doesn't matter to me if it's flight critical or not. How many test articles am I creating? And am I creating that same amount of test articles for every part? And are they being shipped off and evaluated? Can you talk a little bit more what it looks like practically for people that have not done additive manufacturing to go through that startup process? What kind of things can they expect to be doing?
Okay. So I'm going to go back and show you a couple slides. Okay. So to validate the process, let's say I'm going to validate that I have the correct machine parameters. Let's take a look at this titanium build. And the reason you want to build it this way is well, there are several reasons, right? So let's say if all parts, what you have here is 1, 2, 3 tensile specimens in height. So if all your parts were short, you would only have to build tensile specimens the height of your part, right? But if you have a tall part, you want tensile specimens from the base plate to the very top of the part, because what you want to know, particularly in alloys like titanium or aluminum, are you getting the exact same mechanical properties at the top of the build as you are at the bottom of the build, right? Because aluminum, particularly aluminum, when you have really long builds, it starts to age. And that is this truth also with certain stainless steels. So you may have a build here that's 4 days, right? So this part of the build down here has been exposed to 200°C build plate temperature for days, whereas the part of the build up here may be exposed to a little bit less than that for 8 hours, right? So when you turn the machine off and cool it down, there's powder all around this, right? So it's an insulating blanket. These will not cool. These will cool. And so what you want to know does that make a difference for the alloy you're doing? So now I'm going to go back in here. If you send this presentation out, this is, okay, so let's look at this part. This is a mid-engine frame that we were printing for a customer in Europe, right? So as you can see, you're going to build specimens all the way up, all right? Now, in this particular case, you're going to build at least one and maybe two destructive parts. So you're going to build inside, you're going to cut this part up, and we're going to cut tensile specimens out of these parts, because what we want to know is, does the mechanical properties of the part equal the mechanical properties of the test specimen? Now, you don't see it here, but in a approval process, you're going to build these tensile specimens not only around this plate, but you're going to build them inside the part all the way up from top to bottom. And you're going to test, you're going to look at the microstructure of the part, and you're going to look at the microstructure of the specimens, and you're going to tensile test all of them, right? So on a part this big, you may get 20 or 30 tensile specimens just out of this region right here. You may take some out of this region right here. You want to know about orientation effect. So you see this rim that goes around here. You may cut some specimens out of that rim. Once it's qualified, you only have to do that during the qualification process. During the production runs, it's up to your customer and your quality department, but you may only have to build test specimens on the side. And that may seem like a lot, but the simple truth is, if you did a casting, and we've been doing this for 60, 70 years with castings, you always cast destructive specimens like this to the side of the part. You always do that. And you pull them and you look at the microstructure and you make a determination, is that a good part? And for the first casting or the second casting, you cut it up and you look, you do the exact same thing. It's no different with additive manufacturing. Excuse me.
Great.
That answer your question?
It does. Yeah. Thank you.
So if you send this presentation out,
Mhm.
I always have this appendix in the back to tell a little bit more about SLM, but it's more salesy. And I know you didn't want that, right? But
Right.
There's some great slides back there to help explain answers to questions that you just asked.
Okay, cool. I've got one more final question for you, if you would, Don. Can you talk to me about big data? You talked about the databases, and certain customers out there may require
Right.
potentially that data set. How big are we talking, and how do people store those or transfer those to their customers?
Okay. So there are systems out there. So SLM sells laser power monitoring and melt pool monitoring, right? And we look at these things continually. And if you have a big build, you're looking at terabytes of data. And if you have a facility, I was in a facility once that had over 100 printers. So if they were doing all of this data, you're not talking about terabytes, you're talking about what is the next level? Petabytes, right? Right. So, and if you take a digital photo, there's software being developed now where you take a digital photo of every layer. And the way it's supposed to work is that the computer will look at that digital photo and compare it to the CAD file at that same level and identify if there's an anomaly, not if anything's wrong. So you're looking at huge amounts of data. And so then the next question is, what do you do with it after you have it? I think the industry is still trying to figure that one out, in that, do I need data from every layer, or do I need data from every 100 layers or every 1,000 layers, Or do I just write a computer program that says, hey, if there was an anomaly in the shape, then I'm going to send in the final report, everything was good except layer 1038, right? You need to look at that. It doesn't mean that it is bad. It just means that it did not match the exact same geometry as the CAD file. And it may, depending on the sensitivity, it may be 2 or 3 thousandths one way or 2 or 3 thousandths another way. Maybe the melt pool monitoring did a flip. Maybe the oxygen level went up 100 thousandths more than it should have, parts per million. You know, there's a lot of data, but you ask a very, very good question. And I don't think everybody wants data, but we don't really know yet what to do with it after you got it. Right. So you look at some of these things that our friends in the space industry are printing, where it might take 2 weeks to print a part. My God, that is just an enormous amount of data. And it would take you an enormous amount of time to evaluate it. This has to be done with software. You can't rely on human intervention to look at this stuff and figure out good from bad.
Right. Well, Don, thank you so much for the amazing presentation today and teaching us all quite a bit more about what it takes to actually get into additive manufacturing. And then once you do, what you're going to need to do to be successful. And we're very grateful for you, Emily Winthrop, and the entire team there at SLM. And it's nice to know that when companies get into this, they've got some great resources like your team there that can help them through these things and point them directions and provide those various resources that you shared today. So Don, thank you so much for being here and answering folks' questions today. So I'll work with you and your team on making sure we can get some material out to the folks that joined us today. And we look forward to part 3 coming up in May. So
yeah, well, thank you for the invitation, and we're always here to help members of the PNAA. So reach out to us at any time.
Absolutely. Yeah, and all the folks that we've worked with at SLM have just been so fantastic and so easy and kind to work with. So thank you all for all your help at SLM. We appreciate it. So.
Okay, great. Thank you.
Yeah. Well, with that, we are going to conclude. We are going to have some upcoming events. Keep an eye on the PNAA website, and on the left side there over events, you can hover and see the calendar and see all the different events that we have coming up. We're going to be doing one coming up actually on May 6th, Foundations for the Future. We're going to be talking about this new organization that's helping bring up students into the space industry in particular and some of the adjacent industries. So mark your calendar for May 6th on that. And then otherwise, we look forward to seeing you hopefully on Friday at Factory Fridays and our upcoming events here in the months ahead. So thanks everyone. Thanks again, Don, and everyone at SLM. And we look forward to seeing you soon.
Okay. Have a good day.
Take care. See ya.
Thank you, everyone.
Thanks.